The mechanism of mitomycin-C. Mitomycins are a series of actinoplastic antibiotics that are produced from the culture filtrate of Streptomyces colispitosis, which is a species of actinobacteria. Actinoplastic means that these mitomycins are used to prevent or inhibit the development of tumors. These mitomycin antibiotics were first discovered by Hada et al. At the Kitasato Institute in Japan in 1955. There are currently 17 known mitomycins, and 16 of these exhibit biological activity, in particular antibiotic and anti-tumor activity. Mitomycin-C is highly stable and has the most potent anti-tumor activity of all the mitomycins. Mitomycin-C is beneficial in the treatment of many types of solid tumors and hematologic malignancies. It was first approved for treatment in 1963 in Japan and has since been approved around the world in more than 80 countries. So what is mitomycin-C used for exactly, and what does it do? It is an anti-tumor antibiotic which produces its anti-cancer effects by binding to DNA and inhibiting the production of proteins that are necessary for sustaining the life of a cell. Mitomycin-C cross-links the complementary strands of the DNA, which is lethal enough to cause death of a bacterial cell. The mechanism of this will be talked about in a bit. Because of these biological effects, mitomycin-C can be widely used in cancer chemotherapy. Therefore, it is important to understand its mechanism of action, the identity of the DNA adducts it forms, and the structure of the DNA-MC complex. The mitomycin-C molecule has a quinone group, which is a very good Michael acceptor. The OMe group is prone to elimination, and the aziridine ring is electrophilic and acid sensitive. Mitomycin-C itself does not react with DNA. The reactivity of the two requires enzymatic or chemical reduction. The mechanism starts with the reductive activation of the quinone to the hydroquinone form. The reaction of mitomycin-C with thiols is a hypothesized autocatalytic reaction for the reduction. Manuel M. Paz proposes an initial conjugate addition of thiolate to the quinone. From this, a base removes one of the hydrogens from a thiolate, such as 1,3-propane dithiol. This dithiol then attacks carbon 1, turning the double bonded oxygen into an O-. This O- then picks up a hydrogen. 2 electrons from the other double bond O grabs a hydrogen from the dithiol, which gives the hydroquinone complex and a disulfide compound as products. A base then extracts a hydrogen from carbon 7, shifting the electrons, forming a double bond between carbon 7 and 8, and eliminating the OMe group to give an MEOH and generate a leucoaziridinomitosine. The carbon 9 aziridine and the carbon 12 carbamate groups are 2 alkylating functions that can alkylate 2 nucleophiles of DNA, resulting in the MC-DNA crosslink. A base removes the hydrogen from the OH group on carbon 6. Following the arrows, this forms a double bond between carbon 8 and carbon 9, shifting the 2 electrons and putting them onto the nitrogen, which will pick up another hydrogen. This causes the aziridine ring to open, which produces the unstable vinylogous quinone methide. This creates high alkylating reactivity at carbon 9, which reacts with the DNA nucleophile, in particularly deoxyguanosine residues. 2 electrons from the nitrogen group from guanine will attack carbon 9, shifting the electrons to the double bonded oxygen on carbon 7. This then picks up a hydrogen. This will result in the following compound. Activation of one alkylating agent forms a monoadduct. A second alkylating center develops at carbon 12 by reverse Michael elimination of the carbamate. Electrons from the nitrogen shift, creating a double bond, and then kick off the carbamate group. This activated mitomycin-C molecule will either react with water, creating a monofunctional adduct, or attack DNA again at carbon 12, resulting in several bifunctional adducts. If the alkylating reactivity of carbon 12 allows for reaction with another DNA nucleophile, it will either react with another guanine or it will attack the guanine on carbon 9, resulting in a crosslink adduct. Either way, the adduct will then oxidize the 2 OH groups, giving the final monofunctional and bifunctional adduct products. Here is a display of the 6 major mitomycin-C adduct products. In conclusion, mitomycin-C is a sufficient DNA cross-linking machine. These DNA monoadducts and cross-links of mitomycin-C can block transcription and DNA replication and cause cell death in malignant tumors. This mitomycin-C antibiotic is a wonderful and useful chemotherapeutic agent used to treat upper gastrointestinal cancers, anal cancers, breast cancers, and bladder cancers, to name a few. With further research and understanding of the drug, mitomycin-C will eventually be able to treat more than just tumors. Thank you.